Welcome back, everyone, to the deep dive. We're all about exploring new ideas, and today we're doing something a little different, something you might not think of as philosophy right away. But it really gets at those big questions, those core philosophical questions about what we can actually know, what truth is, and how we can be sure about anything at all.
Yeah, it's like we're putting on our philosopher hats, but instead of sitting in armchairs and pondering the meaning of life, we're going to be thinking like the mathematicians and logicians we'll be discussing today. These folks were grappling with some really foundational issues in their fields, which, when you get down to it, are deeply philosophical.
Exactly. It's about getting to the bedrock of knowledge itself. And for this deep dive, we're going deep, deep into the world of mathematics and logic.
And it might seem kind of, purely technical at first glance. But trust me, these fields are built on a whole history of philosophical inquiry, a lot of back and forth, even struggles. These thinkers were wrestling with some really tough questions, like what does it even mean to be certain about something in mathematics? And those questions, they actually ripple outwards and have a huge impact on how we understand knowledge in general.
That's what I love about this stuff. It's like the more you dig into these seemingly niche areas, the more you realize they're connected to these massive philosophical questions about the universe and our place in it.
Totally. And our guide for this intellectual journey, our map, if you will, is going to be the Stanford Encyclopedia of Philosophy entry on proof theory. Now, I know. Those words philosophy, proof theory can sound a bit intimidating.
A little bit, yeah.
But bear with us, because this is a fascinating area that really digs into how we establish certainty, especially in these very rigorous structured systems we call formal systems.
It's like, how can we be absolutely sure that something is true when we're working with these systems of symbols and rules?
Right. And that's our goal today, our mission, to pull out those key insights from proof theory that shed light on how we achieve certainty, and, equally important, to really explore the limits, the boundaries of even the most powerful formal systems. Because even with all our fancy logic and symbols, there are some things we just can't prove.
Okay, so let's get into it. Our source starts by saying that proof theory, it wasn't just some theoretical invention that mathematicians came up with out of the blue.
Mm.
It actually grew out of the real day-to-day work that mathematicians were doing, wrestling with some really fundamental problems back in the 19th century.
Yeah, you can almost picture them hunched over their desks, scratching their heads like, wait a minute, what are we even doing here? What are the rules of the game? It's almost like they were forced to become philosophers, to really question their own assumptions just by virtue of doing their work.
Right, exactly. And the 19th century was this incredibly dynamic period for mathematics. Our source talks about this shift towards more abstract thinking, the rise of set theory as a potential foundation for all of mathematics, and a much greater focus on logic itself, not just as a tool, but as a subject worthy of study in its own right.
Totally. It was a pretty radical shift.
Hmm.
And as math became more abstract, more about these general structures and relationships, mathematicians were forced to confront these heady philosophical questions about, like, what are we even talking about here? What is the nature of these mathematical objects we're working with? Are they real? Do they exist outside of our minds?
Yeah, big questions. And it wasn't exactly a smooth transition, was it? The source mentions some serious debates going on between mathematicians like Dedekind and Kronecker. They were on opposite sides of some pretty significant philosophical issues.
Absolutely. It was a real clash of titans. I mean, they were debating things like whether certain undecidable concepts were legitimate, the very idea of infinite objects, and the validity of those tricky non-constructive proofs that seem to prove something exists without actually showing you how to find it.
Oh, right. Like, I can prove this thing exists, but I can't tell you what it is or how to find it.
Exactly. It's a very strange kind of proof from a philosophical standpoint. It's like saying, I know there's a treasure buried somewhere, but I have no idea where to dig.
Uh-huh. Yeah. So, out of this period of questioning and debate emerged this incredibly influential program spearheaded by the great David Hilbert. Our source calls it, and I love this phrase, a philosophical quest for certainty. And when we talk about Hilbert, we can't avoid talking about the axiomatic method, which was central to his program. Can you give us a quick rundown of what that is and why it was such a powerful idea?
Sure. So the axiomatic method, it's all about establishing a clear and rigorous foundation for a system of knowledge. You start with a small set of basic assumptions, which we call axioms, and then you use logic, very carefully, to derive all the other truths of the system from those axioms.
It's like building a logical structure brick by brick with the axioms as the foundation.
Precisely. And Hilbert, He saw this method as absolutely essential, not just for math, but for any field where we want to be certain about our knowledge. He believed that if we could formalize all of our reasoning in this way, we could then analyze those systems for consistency to make sure they don't lead to any contradictions.
Because a system with a contradiction in it, that's like a house built on sand.
Right.
It's fundamentally unstable.
Exactly. And Hilbert wasn't just talking about this abstractly. He looked at his own work on the arithmetic of real numbers and Euclidean geometry as examples of how this axiomatic method could be used to put these foundational areas of math on a really solid footing.
And he wasn't just content with applying it to existing areas of math, right? He had this much grander vision, this programmatic direction for the future of mathematics. What was the ultimate aim of Hilbert's program?
Hilbert's big dream, you could say, was to formalize all of higher mathematics within a single, unified axiomatic system. And crucially, he wanted to prove, beyond any shadow of a doubt, that this system was consistent, that it wouldn't lead to any logical contradictions. This was a deeply philosophical goal, to really secure the foundations of math and eliminate any possibility of uncertainty.
It's like he was trying to create this ultimate unshakable foundation for all of mathematical knowledge.
Exactly. And to do this, he really emphasized these very basic constructive methods of proof. His idea was that if we could prove the consistency of this grand mathematical system using only these absolutely bedrock finitist methods, then we'd have a guarantee and absolute certainty that the whole structure was sound.
And to get this done, Hilbert had a key collaborator, Paul Bernays, who played a critical role in developing these very restricted, constructive approaches that were central to the program. The source specifically mentions finitist arithmetic and finitist logic. What's the core idea behind these frameworks?
So Bernays, he took an incredibly strict, you could even say minimalist, approach to what counts as valid mathematical reasoning. Finitist arithmetic was this very limited system, dealing only with objects and operations that you could concretely construct in a finite number of steps.
Like you can actually count them out one by one.
Right. And finitist logic was the corresponding logic that you could use to reason about these finitist objects. No fuzzy, infinite stuff allowed.
Okay, so the initial strategy was to try and prove the consistency of more powerful mathematical systems using these very limited finitist tools. And there were some early attempts by mathematicians like Ackermann and von Neumann. How did those go?
Yeah. They were making some real progress, at least for a while. For a time, there was genuine optimism that they might actually pull it off, prove the consistency of at least some parts of arithmetic using only these finitist principles. Ackermann, in particular, he was developing some really clever techniques for manipulating formal proofs, which was a big step forward.
But there was a catch, wasn't there? Like, these early attempts were only able to handle a limited part of finitist math. The real challenge was proving the consistency of what Hilbert called transfinite logic, the parts of math that deal with infinity and all those mind-bending concepts.
Right, and that's where things got really tricky. Hilbert's strategy involved introducing what he called the transfinite axiom and using these things called epsilon terms as a way to kind of tame the infinite. The idea was that you could, in principle, assign concrete finite values to these epsilon terms and thereby ground those more abstract infinite parts of math in something more concrete.
It's like he was trying to build a bridge between the finite and the infinite.
Exactly. And Ackermann continued working along these lines, and for a while it seemed like the consistency of at least elementary arithmetic might actually be within reach. Our source even mentions a theorem, Theorem 1.1, which gets at the heart of why this was so philosophically important. It basically says that if you can prove the consistency of a theory using only finitist methods, then any real concrete statement that you can prove within that theory can also be proven directly using those finitist methods.
So it's like a guarantee that even if we use these more powerful abstract methods in math, as long as we have this finitist proof of consistency, we can be sure that those results are ultimately grounded in something solid, something we can really trust.
Precisely. It's like having a safety net, a way to ensure that even if we venture out into the dizzying heights of abstract math, we always have a solid foundation to fall back on.
But then enter Kurt Gödel and his absolutely groundbreaking incompleteness theorems.
Yeah, Gödel, he kind of dropped a bombshell on the whole mathematical world. His theorems, especially the second one, showed that any sufficiently powerful formal system that can do basic arithmetic can't actually prove its own consistency.
So it's like a fundamental limitation, a built-in blind spot in these formal systems.
Exactly. It was a huge blow to Hilbert's program. It meant that even if Ackermann and von Neumann had been completely successful with their attempts, their results would always be limited by this inherent inability of a system to fully grasp its own consistency.
So it wasn't just a technical problem, it was a fundamental limitation on the very nature of formal systems.
Right. Gödel essentially showed that there are certain truths about mathematical systems that those systems themselves just can't capture. They're always going to be incomplete, always going to have these blind spots.
Okay, so Hilbert's grand vision of this completely formalized, consistent foundation for all of mathematics, that dream was kind of shattered by Gödel's work.
In a sense, yes. It meant that the original goal, proving the consistency of full arithmetic using only finitist methods, was simply not possible.
But the source does mention that even Gödel himself thought there might be other ways to go about this, to find a solid foundation for mathematics, even if it meant going beyond strict finitism.
Yeah, even with his own earth-shattering results, Gödel didn't completely give up on the search for a secure foundation for mathematics. He suggested that maybe we needed to broaden our horizons, to explore these constructive methods that went beyond the very narrow limitations of finitism.
Like, maybe there's a sweet spot, a kind of middle ground between strict finitism and the full power of classical mathematics.
Right. He was particularly interested in intuitionism, which is a different philosophical approach to mathematics that we'll talk about in a minute. He saw it as a potential path to grounding classical math, even if he had some reservations about some of its more abstract aspects.
Okay, so that brings us to these alternative philosophical perspectives, constructivism and intuitionism. Can you give us a quick overview of what these are all about and how they differ from the classical approach that Hilbert was working with?
Sure. So both constructivism and intuitionism, they share this core philosophical idea that mathematical objects and truths need to be, in some sense, constructed, built, or demonstrably shown to exist.
They're like, show me the math.
Haha, exactly. They reject the idea of non-constructive proofs, so those ones that say this thing exists without telling you how to find it. And they also have some issues with the unrestricted use of the law of excluded middle, which is this classic logic principle that says every statement is either true or false.
So it's like, for them, it's not enough to just say something exists or to say it's either true or false. You need to actually show it, demonstrate it in a concrete way.
Right. And they have different philosophical reasons for this. Constructivists tend to focus on the idea that mathematical objects are, in some sense, mental constructions. So to say something exists mathematically, you need to be able to, in principle, construct it in your mind.
It's like if you can't build it, it doesn't exist, at least not mathematically.
Yeah, kind of. And intuitionists, they have a slightly different take. They see math as being about mental constructions as well, but they focus more on the idea that mathematical proofs are about providing compelling mental evidence for a claim.
So it's not just about manipulating symbols on a page. It's about actually convincing someone, showing them why something must be true.
Exactly. And the source specifically mentions intuitionistic logic in mathematics, which is built around this thing called hating arithmetic, HAA. How does this framework differ from the standard classical arithmetic we know and love, which is usually formulated as piano arithmetic, PA?
Yeah, break that down for us.
So intuitionistic logic, it's kind of like a more cautious, more demanding version of classical logic. It operates under the stricter interpretation of the logical connectives, like or and there exists.
Like those little symbols that connect mathematical statements together.
Exactly. So in classical logic, you can say something like A or B is true, even if you don't know which one is actually true. You know, one of them has to be true, so the whole statement is true.
Right.
But in intuitionistic logic, to say A or B is true, you actually have to have a proof of A or a proof of B. You can't just say one of them must be true without knowing which one.
Oh, interesting. So it's like in intuitionistic logic, you need more concrete evidence.
Exactly. And it's the same with existential statements, like
Yeah.
there exists an X such that. To prove that in intuitionistic logic, you actually have to be able to produce that X, to point to it and say, here it is. You can't just prove it indirectly like you can in classical logic.
So it's a much more hands-on, concrete way of doing math.
Exactly. Now, you might think that this stricter logic would make intuitionistic math weaker than classical math. But there's this fascinating result discovered by Gödel and Gensen called the negative translation, which shows that it might actually be the other way around.
Wait, really? So intuitionistic math, with its stricter rules, could actually be more powerful in some ways.
That's what this result suggests. This negative translation, it's basically a way to take any formula or proof in classical piano arithmetic, PA, and systematically transform it into an equivalent formula or proof in hating arithmetic, HA.
So it's like a way to translate between these two different mathematical languages.
Precisely. And Theorem 1.2, it shows that this translation preserves truth in a really strong sense. It says that PA can actually prove the equivalence between any formula and its negatively translated counterpart. And if PA proves a formula, then HA proves its translation.
So what does this mean in terms of the consistency problem that Hilbert was so concerned about?
Well, because the negative translation lets us embed classical arithmetic within intuitionistic arithmetic, if we assume that HA is consistent, then we get a kind of indirect guarantee that PA is consistent as well.
It's like if the more demanding system is solid, then the less demanding system must be solid too, right?
Precisely. And this was a pretty big deal philosophically because it suggested that maybe you could provide a foundation for classical math, even if it wasn't based on those strict finitist principles that Hilbert originally had in mind.
Right. It opened up this whole new way of thinking about the foundations of math.
Yeah, and the source goes on to mention a bunch of other constructive frameworks beyond intuitionism, like arithmetical predicativism, theories of higher type functionals, Fefferman's explicit mathematics, and Martin Luff's type theory.
It seems like acting as a philosopher in this area of math leads to a whole spectrum of different perspectives, all trying to grasp those fundamental questions about how we know what we know in mathematics.
Absolutely. Each framework represents a slightly different take on what constitutes constructive and what kinds of mathematical objects and reasoning are, kosher. Like arithmetical predicativism, it's really concerned with avoiding these circular self-referential definitions that are common in classical math.
Those always make my head spin.
Haha, I hear you. And then you have things like Pfefferman's explicit mathematics, which tries to formally capture the idea of explicitly given objects, the kind of things you can point to and say, here it is.
Okay, so lots of different approaches to being constructive. But how do we compare these different systems? How do we figure out which one is like more powerful or more expressive?
That's where the idea of proof theoretical reduction comes in. It gives us a way to formally compare the fundamental strength of different mathematical theories. The source gives a precise definition, but the basic idea is this. You try to show that one theory, T1, can be reduced to another theory, T2.
What does it mean to reduce one theory to another?
It means you find a way to systematically translate any proof in T1 into a proof in T2 using only very basic, uncontroversial methods.
Like a translation that everyone agrees is legitimate.
Right. And if you can do that, it suggests that T2 is at least as strong as T1 because it can prove everything that T1 can prove, and maybe even more.
Okay, that makes sense. And if two theories can be reduced to each other, then they're considered to have the same proof theoretic strength.
Exactly. And what's really interesting is that in practice, when two theories are proven to be equivalent in this way, they often end up proving the same pi 2 sentences. These are statements of a particular logical form, often expressing some kind of general pattern or regularity in mathematics.
So it's like they capture the same kind of mathematical truths.
Right. And this gives us a way to compare not just the technical strength of different systems, but also their underlying philosophical commitments, what kind of mathematical world they describe.
Okay, let's move on to another really important development in proof theory. These new logical calculi that were developed especially by a logician named Gerhard Gentzen. He came up with these systems called natural deduction and sequent calculi. How did these differ from the more traditional axiomatic systems?
So Gentzen, he was really interested in making logic reflect the way mathematicians actually reason in practice. Traditional axiomatic systems, they tend to be very formal, very abstract. You start with these axioms, and then you use these very rigid rules to derive other statements.
It can feel a bit like, manipulating symbols on a page without really understanding what's going on.
Right. And Gintzen's systems, especially natural deduction, they were designed to be more intuitive, more like the way we naturally think about proofs.
And the key innovation here was the idea of having specific introduction and elimination rules for each logical connective.
Exactly. So for each connective, like and or implies, you have a set of rules that tell you how to introduce that connective into a proof, and another set of rules that tell you how to use or eliminate that connective to derive further conclusions.
So it's like a more dynamic, more flexible way of reasoning.
Exactly. And in sequent calculi, which is another system that Gentzen developed, there's this really important concept called cut elimination, also known as the Hauptsatz.
What's a cut in this context, and why is getting rid of them so important?
So a cut, it's basically a rule that lets you use an intermediate result in a proof and then discard it. It can make proofs shorter and easier to write down, but it can also obscure the underlying logical structure of the argument.
Like a shortcut that hides some of the steps.
Right. And the Hauptsatz, this cut elimination theorem, it shows that any proof, no matter how many cuts it uses, can be transformed into an equivalent proof that doesn't use any cuts at all.
So it's like cleaning up the proof, making it more transparent, more elegant.
Exactly. And this has a really important connection to proving consistency. Corollary 2.5 in the source states that if a logical system has this cut elimination property, then it's impossible to derive a contradiction within that system.
Because a cut-free proof, it lays bare the logical structure of the argument, so you can see directly that there's no way to get from the axioms to a contradiction.
Precisely. But, as the source points out, cut elimination becomes much harder when you start dealing with mathematical theories that have axioms asserting the existence of mathematical objects, like Peano arithmetic, which we talked about earlier.
Right, because those axioms, they kind of disrupt the nice, clean structure of the sequent calculus, which makes cut elimination much harder.
Yeah, those existence axioms, they're like these little gremlins that can mess up the whole cut elimination process.
Okay, now we're getting into some pretty heavy stuff, but it really shows that even basic arithmetic, which we all learn in school, rests on this incredibly complex and philosophically rich foundation.
Absolutely. It's all about digging deeper, questioning those assumptions, and seeing what lies beneath the surface.
So let's dig a little deeper now and talk about ordinals, which the source describes as a way to count beyond the finite. Why have ordinals become so crucial in proof theory, especially when dealing with systems like Peano arithmetic?
So ordinals, they're basically a way to extend the idea of counting to infinite sets. They give us a way to measure the size or complexity of well-founded orderings, and that includes the very structure of mathematical proofs themselves.
It's like we need a bigger measuring stick when we're dealing with infinity.
Exactly. And in proof theory, especially for systems like PA where full cut elimination doesn't hold, ordinals give us a way to assign a kind of complexity measure to proofs.
Like how difficult it is to prove something.
Right. And Gensen, when he proved the consistency of Peano arithmetic, he did it by assigning ordinals to hypothetical proofs of contradiction. He showed that any such proof would have to involve an ordinal greater than or equal to a certain transfinite ordinal called var epsilon.
And this var epsilon, it's a special kind of ordinal, right?
Yeah, it's a pretty fascinating one. It's defined as the smallest ordinal greater than 0 that satisfies a certain equation involving exponentiation with omega, which is the first infinite ordinal. It's, a bit technical.
We'll spare the listeners the details. Haha.
But the point is that this particular ordinal, for epsilon, it's deeply connected to the proof-theoretic strength of Peano arithmetic. Gensen showed that PA can prove transfinite induction up to any ordinal less than var epsilon, but not up to var epsilon itself.
So it's like var epsilon marks a kind of boundary, a limit on what PA can prove.
Precisely. And more generally, the proof-theoretic ordinal of a theory, it gives us a way to quantify how non-constructive or ideal that theory is. It's a measure of how far beyond those basic finitist principles it goes.
Okay, so we've got these ordinals, which are helping us measure the complexity of proofs and the strength of different theories. But the source also mentions these even more mind-bending concepts, infinitary logics and the omega rule, which are ways of going beyond the limitations of finitary systems. This sounds pretty wild.
It is. It's like we're breaking the rules of the game, allowing for proofs that could potentially have infinitely many steps.
Whoa.
Yeah, the omega rule, it lets you infer a universal statement, like, for all x, such and such is true, if you have a proof for every single case, even if there are infinitely many cases.
So it's like instead of proving something for all cases at once, you prove it for each case individually, even if there are infinitely many of them.
Exactly. And this opens up a whole new world of possibilities.
Yep.
But it also raises some deep philosophical questions about what it even means for a proof to be infinite.
Right. It kind of stretches our intuitions about what a proof should be.
Totally. But it's a really interesting area of exploration, trying to understand the limits of finitary reasoning and whether we can go beyond them in a meaningful way.
Okay, so we've covered a lot of ground here, from Hilbert's program to ordinals to infinitary logic. But let's shift gears a bit and talk about systems that are even stronger than basic arithmetic, like second-order arithmetic, also called analysis, and theories of iterated inductive definitions. Why are these more powerful systems so important from a philosophical perspective?
So these systems, they allow us to formalize a much larger chunk of classical mathematics. Second-order arithmetic, in particular, lets us talk about things like real numbers, limits, continuity, all these concepts that are central to calculus and analysis.
It's like we're moving up the ladder of mathematical abstraction.
Exactly. And from a philosophical perspective, these systems raise even deeper questions about what we consider to be acceptable mathematical objects and methods of proof. Like in second-order arithmetic, we have this thing called the comprehension principle, which lets us define sets based on arbitrary formulas.
So we can talk about sets of sets, sets of sets, and so on.
Right. And that leads to some really tricky philosophical issues about, like, what is a set? Do these highly abstract sets really exist? What's the relationship between language and mathematical reality?
Deep stuff.
And then there was this really important conjecture by Turcuti about cut elimination in higher order logic, which is a system that's even more powerful than second order arithmetic. If this conjecture had been true, it would have meant that a vast amount of classical math, including analysis, was consistent.
So it was a really big deal for the foundations of mathematics.
Absolutely. And while there has been significant partial results and semantic proofs of cut elimination in these higher order systems, the methods used are often non-constructive, which has led to some debate about whether they really satisfy the spirit of Hilbert's program.
Right, because Hilbert was all about those constructive methods, those absolutely certain proofs.
Exactly. And the source also mentions this really cool program called reverse mathematics, which tries to figure out the minimal set of axioms you need to prove specific theorems in ordinary math.
It's like stripping down a theorem to its bare logical essentials.
Yeah, it's a really elegant way to figure out the hidden philosophical assumptions that are lurking beneath different areas of math. And by doing this, we can get a better understanding of the fundamental principles that different branches of math rely on.
Okay, so we've gone from Hilbert's program to ordinals to infinitary logic to these incredibly powerful systems like second-order arithmetic and beyond. It's clear that the search for a solid foundation for mathematics, it's an ongoing journey, a constant process of exploration and discovery.
Absolutely. And it's not just about finding the right technical tools. It's about grappling with these deep philosophical questions about what math is, what truth is, and what we can know with certainty.
It really makes you think about the different philosophical perspectives we've encountered today, finitism, intuitionism, predicativism, and how they each represent a unique way of acting as philosophers when faced with these foundational questions.
Exactly. And that brings us to a final thought, something for you, our listeners, to ponder. Could the limits of formal systems, the fact that they're always going to be incomplete, as Gödel showed us, tell us something profound about the nature of human understanding itself?
Like, are there inherent boundaries to what we can know, no matter how hard we try, no matter how sophisticated our systems become?
It's a really deep question, and it's one that continues to drive research in the foundations of math, logic, and philosophy. It makes you wonder about the nature of truth, the power of reason, and the very limits of human knowledge. Thanks for joining us on this deep dive, folks. It's been a wild ride.